Good afternoon. My name is Igor Aharonovich, and I'm from the University of Technology, Sydney. And in the next 10 minutes, I would like to share with you some of my work, our group work on defects in solids and their promise for quantum information processing and quantum photonics. So the title of the talk is The Dawn of Defects. So when we think about the quantum world, we can basically divide it into three components: the quantum sensing, and here really the majority of I will just make a pointer. Majority of the work has been focused around the nitrogen vacancy defect in diamond. It provides you with very luminescent single photon source, but also optical access to the spin state, which means that you can optically manipulate and read out the spin of a single defect. And that can act as a sensor for many electromagnetic fields. Of course, you have the field of quantum computing, and here the majority of work these days focused around the superconducting qubits. Quite a few commercial devices have already been made. And of course, there is also a promising approach to use optical qubits or interface between the different nodes with photons. And so this is one of the first works by the group of Rempe, and they demonstrated a network between two trapped ions or trapped atoms that are put in a cavity and interconnected with the channel. And so the vision really is you can build up an entire quantum network where in every node you will have an access to a single photon source and a quantum memory, and ideally the photons will be identical, of course, and you can then construct your network. This whole thing is basically underpinned and envisioned to provide a foundation for your quantum internet. Again, when you have nodes and they're interconnected with some optical channels, and there are very nice reviews by Jeff Kimball and more recently by Ronald Hansen. And the final application is quantum communication. Quantum communication does not require as much demand from your source apart from purity and polarization. So if your source is highly pure, you can potentially perform quantum communication protocols such as quantum cryptography, employing, for example, the BB84 protocol or others. So for this application, you basically only need a very bright source of photons, of pure single photon source. So of course, if we want to think about the quantum internet and this integrated network for quantum computing, ideally we would like to have a source that will be a solid state. It will just be much easier to scale things up. And so if you look about 10 or 11 years from ago, in terms of solid state single photon sources, you're pretty much limited to two platforms, the NV Center in Diamond, that is now quite common, quite famous specifically for sensing applications, which has a very broad emission, which for photonics, scalable photonics is not ideal because it's broad and your useful signal is only here in the zero photon line. Only this 4% of the photons can provide you kind of coherent photons. So not ideal. And your arsenide-based quantum dots. So already very pure sources have been developed for some years. So that's in 2009. And so fast forward into 2020, we now have a vast library actually of single photon sources. So starting with defects in carbon nanotubes and graphene quantum dots. Of course, your single molecules are excellent sources. And quantum dots had a massive advance, quite a few groups putting a lot of effort. And in fact, you can now even purchase commercially an integrated single photon source based on quantum dots that is put in a Bragg cavity and it's electrically triggered. So the technology matured quite a bit. Unfortunately, most of them still require cryogenic temperatures for the pure quantum dots. Now, our group interest lies within the Scholar centers in solid, and that's where the NV Center in Diamond really pioneered that field. And since then, a lot of effort has been done to study even other platforms like the silicon carbide, quite a few defects, rare earths in YAG crystals, and some other outliers like the zinc oxide. So this system is great because the defects are embedded very deep within the bandgap. So if you look at the bandgap of a few materials, for example, diamond, the bandgap is very large, it's about 5.5 eV, and the defects, your quantum, artificial quantum system actually resides inside, so it doesn't interfere with any of the bands. And this protection, that's what yields its room temperature operation and also provides you this solid state platform for single photon sources. So recently we started to look into HBN, and the advantage of HBN here, of course, it's also a large bandgap material, but a unique property of HBN as compared to pretty much all the other systems here is that its ability to be exfoliated into 2D layers, into atomically thin 2D layers. And so this is quite an advantage because you can think of, first of all, making devices or kind of assembling devices in the Lego style, instead of, for example, very expensive growth chambers like you need to do with gallium arsenide. And then, of course, you can also put them, integrate them very easily with cavities. So here's an early example from a 2D material that's not HBN, but other materials that were integrated with photonic crystal cavity and with a Bragg cavity. And of course, 2D materials also give you quite a variety of new phenomena. So this is an example of Moiré patterns, and you can look at the references here for quite a few works. So as I mentioned, our interest is within HBN and finding single defects in this family of 2D materials, in HBN specifically. And so what we did, we started to grow our own HBN, and the growth is very simple. You can just do it in a very conventional tube furnace, and the results are quite promising because you can see that most of your emitters fall here within around the 600 nanometer range. And the emitters are very, very narrow, unlike the nitrogen vacancy center and diamond, for example. And of course, they're also single photon sources, as evidenced here by this second order autocorrelation function. So there are also many groups that are now working on it. So I just mentioned here a few in case you want to kind of Google it yourself. And the origin of defect is still under debate, but we are now almost 100% convinced that it's related to carbon impurity with HBN. And here are some potential geometries, such as the C2CN, where you have two carbon atoms sit on the boron and one on the nitrogen, or vice versa, two carbon sites sit on the nitrogen and one on the boron, or maybe some sort of an anti-site where the carbon sits nearby missing vacancy. So this is still under investigation, but the origin is most likely to be carbon. Now, as I mentioned, the advantage of these 2D materials is that you can easily lift it out and put it on any other device or any other platform. And so indeed, you can easily integrate it with photonic structure to enhance light collection and to realize per-cell enhancement. So this is kind of your fundamental pathway towards achieving on-chip integration. And so here you can grow this HBN and then put it on a silicon nitride, for example, and pattern your devices from silicon nitride. So here you can see a 1D nanophotonic cavity, and you don't see the HBN, of course, but it's inside. And you can see that remarkably, the quality factor of the cavities without the HBN and with the HBN does not degrade. So you can easily incorporate this HBN within the photonic cavities, and you can then measure quite strong per-cell enhancement. So this is actually a single photon source integrated and coupled to a cavity mode. You see it's very, very narrow, and it's also a single emitter, of course. And we estimate a per-cell enhancement of about 20. So that means you emit 20 times more. You can think about this emitting 20 times faster, 20 times more into this particular mode, and 20 times more photons that you can collect. So this is really the first step towards this scalable photonic network, where each node is basically an HBN single source coupled to a cavity. So, and of course, there is a question about the spin. Well, so these defects that I showed you, they have some sort of spin access, but not that great. But HBN offers a different defect. So this is the missing boron, so boron vacancy minus, and has a broad luminescence at about 800 nanometers. And this has a very strong ODMR signal, optically detecting magnetic resonance, at about 3.5 gigahertz, which means that you can have an access to a spin state also with HBN, very similar and very analogous to the defects in diamond. So just to clarify, this is not the same defect as I showed you before, but there's just a different emission line that adds to this versatility of the HBN as a platform for quantum photonics and for spin manipulation. So this is very recent data, only from this year. So we know that the ground state splitting is about 3.6 gigahertz. It's the boron vacancy minus, which means it's a missing boron atom, and it's still an ensemble measurement. So we're now trying to engineer this on a single level. So this is pretty much it for this brief overview. So the vision is that we want to fully integrate this 2D quantum system on a single chip, and we can engineer and control single photon emitters in HBN by controllably growing them, and we can tune them, both amenable to Stark shift tuning and strain tuning. And we can also then engineer them in a cavity. So that's the results that I showed you with a hybrid approach where we couple this HBN emitters to silicon nitride. And also I showed you some very quick results on the recently discovered spin defects in HBN. So I would acknowledge, of course, the group and would like to welcome you all to Australia once restrictions are over. We are in Sydney, so it's a very nice place to be. Thank you for your attention.